Now, for the next part, we will move on to part 2 of this lecture. Now, for this purpose, we would like to observe that the concentration of different elements changing, as an example, with changes in the mineralogy. Now certainly there are something you should know that there are different types of different minerals which prefers different ions in their different sites, like niobium is often scattered in the garnet. Scandium is often goes zinced into pyroxenes. Europium, if it is in class state, it can go in the structure of plagioclase feldspar. Now suppose in a system, or suppose in a situation where there are some plagioclase feldspars which are crystallizing from a magma chamber. Now what will happen there is that if the magma has some amount of europium by positive in its in the melt composition, the europium will try to get inside the structures of feldspar, plagioclase feldspar. As a result, the residual magma during fractionation of plagioclase feldspar as a restite, the magma whenever it is trying to go out, or the residual magma which is moving upwards through the crust, it will have a dip in the europium concentration that was present in the parental magma which crystallized plagioclase feldspar. So that's how sometimes we can say from europium concentration, by analyzing the rocks of later stages, that the parental rock or parental magma which has crystallized this rock might have suffered amount of plagioclase feldspar fractionation. Sometimes if there are garnet in the restite, the garnet can take heavy rare earth elements in its structure, thorium, yttrium, etc., etc., as an example, as well as gadolinium, not elements like which are lighter elements like lanthanum, cerium, etc., etc., but the heavy rare earth elements, they enter the structure of the garnet. So if a magma is coming from the partial melting at depth, and at the deeper situation some garnets are crystallized or have remained as restites, the magma which is rising upward will be less concentrated, or will be less richer in elements or these rare earth elements. So normally, obviously, the HREE concentration in the residual magma which is rising, or even niobium concentration, will fall down. As a result, the crystallized rock in the upper sections during this magmatic fractionation, there will be a lack of these elements. So whenever we try to analyze a rock in sequence or later stages of the rock, its composition may give us the restites which had been in the source, or which had been or which were already in the source region. Now this is very important in terms of getting the idea of how these things take place, or why these things take place, like fraction, or how or where these things take place, as an example, fractionation. In case of, on the other hand, suppose in case of a partial melting or batch, or in case a rock is getting molten, suppose in case of a batch melting, which is, it is a chapter from John Winter, the trace element concentration in the liquid which is being separated, the trace element concentration before the melting began, where the partial melting was taking place, and if the wet fraction produced of the melt, it will increase in in with time, probably suppose if it is 0.1, then it will be 1, then it will be 0.9, it will be 1, it will be 1.2, it will be 1.3, it will be 2, it will be 2.5, and at a certain point of the batch melting or the fractionated melt, the melt will try to escape the system. And if we try to analyze a diagram in terms of an element where D is taken as the reciprocal of the Kd, or the fractionation or the partition coefficient, from or in terms of the mineral and the melt, and this is how it is written: the partition coefficient of I in mineral, DIA, and it is Di bar is, it is like this, where the solid concentration, the D is the concentration in the solid and Cl is the concentration in the liquid. So obviously it is taken into account that the much more the S concentration or solid concentration, the D value is much more increasing. That means that the thing is compatible to the mineral phase which is residing in the system or crystallized in the system. And in terms of that, if it is D is 0.001, that means that the concentration of that element in the liquid is high, or rather whenever the magma or whenever the in between the solid, as it is reciprocal, the D is low, this D or in case of this D, that is 0.1, D is 0.5, D is 1, 2, 3, 4, whatever it is, with increasing fraction of the melt by the event of partial melting from 0 to 0.2 to 0.4 to 0.6, they will try to reach a unity. That is final stages of the melting, when the fraction of the melt is summing the amount of the fraction from the rock, then the value of Cl by C0, that is original rock, the concentration of that element in the rock original, and the concentration of the element in the liquid, will be 1 or unity. And if D is 1, that is the partition coefficient is 1, then always in any type of fraction of melt, this will remain a standard, or D will remain 1, because whenever the melting is happening, the element will try to go in the melt as far as will try to stay in the mineral structure equal. So that's why D will remain 1. But if there are changes, like in case D is different or this D is different, they will follow these graphs. And whenever we will try to put these graphs, if we try to build it from an Excel sheet from these data, these will develop you this type of a diagram or a graph with separate D values. However, the fraction of the melt is being changed. You can do this exercise as well. And these are the partition coefficients, that is element entering in the solid versus element residing in the liquid for different minerals. And look at, there are variations in terms of rubidium concentration. In amphibole, the Cs by Cl is much more higher than in case of an olivine. In case of a barium, it is amphibole, barium can enter its structure. Okay. Nickel, the olivine, nickel is partitioned, or nickel tries to partition itself in the olivine much more concentration. Chromium tries to separate itself in clinopyroxene. So these are the states of the different types of trace elements. Barium tries to reside in the alkali feldspar structure. So that's how the fractionation curves or the diagrams can help us when or where should these minerals or did these minerals crystallized. Like with increasing SiO2, the nickel content, if it drops drastically, then we can say that in this region some of the olivine had been crystallized. That's why suddenly there was a nickel drop, or the concentration drop in the nickel content, and zirconium, obviously it will increase with time. So with different elements in different PT regimes and different mineralogies, there will be separate types of outcomes which we might see. And this is the europium anomaly which I was discussing, that whenever we will try to see in terms of different, this is the ratio which, and the diagram and the type of the diagram, it is known as spidergram in igneous petrogenesis or in type of petrogenetic processes. Spidergram, and these values are actually the ratio of parts per million concentrations of lanthanum, cerium, neodymium, samarium, europium, dysprosium, erbium, ytterbium and lutetium in a sample versus in a chondrite value. That is, there might be a drop in the europium concentration, and if there is a drop in terms of the sample, or in the sample in terms of the chondritic concentration, then we might say that there is a source, or the source where the plagioclase feldspar had resided. That's why the magma which had crystallized the sample, which was devoid of europium concentration. However, in terms of the chondrites, the light rare earth elements concentration are very high, and the heavier rare earth element concentration is very low. And that's how the spidergrams can be built, and they can help us to analyze the richness of different rocks in terms of different reservoirs. We can do it in terms of the chondrite value. We can do it in terms of bidogenic ridge basalt value, and with these standards we can analyze that how much, or to what extent the rock or sample is much more enriched or non-enriched in terms of standard samples of bidogenic ridge basalt, or etc. etc. So that's where the basic idea of the practicals of the geochemistry lies, and this is a very small thing I was trying to tell in the class, that is del 18 oxygen value, and this is a ratio in terms of standard mean oceanic water value, and this is the difference, or this is a deviation. Deviation is timed by 1000, and this is known as del value of 18 oxygen in terms of mean value. These types of things can help us, or there is a terminology, or separate reservoirs or separate types of mass fractionations can give us different types of del values for different sources or water. And there is a mean water line or mean global water line, which I will tell you, and this is regarding the radiometric dating. So obviously let's not proceed further. Let's try to keep it simple. How much time is it?